Let's talk about density operators in quantum computing. These are mathematical objects that we use to describe the state of a quantum system. In particular, density operators are used to describe mixed states, which are states that can't be represented as a single pure state. The density operator is a matrix that contains information about the probabilities of different outcomes when measuring a quantum system. The diagonal elements of the matrix give the probabilities of the system being in each possible state, and the off-diagonal elements give information about the quantum coherence of the system. Now, density operators are really useful in quantum computing because they allow us to work with mixed states, which are often encountered in real-world quantum systems. By using density operators, we can perform operations on these mixed states in a way that's consistent with the laws of quantum mechanics. One important thing to note about density operators is that they must be positive semi-definite and have a trace of 1. This is a fundamental requirement in quantum mechanics, and it ensures that the density operator represents a valid quantum state. Density operators are an essential tool in quantum computing, and they allow us to describe and manipulate quantum states in a way that's both precise and efficient. They're an important part of the foundation of quantum computing, and they're used in a wide variety of quantum algorithms and protocols. Let's talk about the properties of density matrices in quantum computing. One important thing to note is that for a two-level system, whether it's a pure state or a mixed state, it can always be described using a density matrix, denoted by ρ. One important property of a density matrix is that it's a positive semi-definite matrix, meaning that all its eigenvalues are non-negative. In addition, a density matrix satisfies the condition that ρ equals ρ squared, which is true if and only if the quantum state is a pure state. The diagonal elements of a density matrix represent the probabilities of measuring each possible outcome if the entire system were to undergo a measurement. In other words, if you were to measure the system in the basis of its eigenstates, the diagonal elements of the density matrix would give you the probabilities of measuring each eigenstate. Another important property of a density matrix is that it has a trace of 1. This ensures that the probability of the system being in any possible state adds up to 1. These properties of density matrices are fundamental to quantum mechanics, and they allow us to describe and manipulate quantum states in a precise and efficient way. By understanding the properties of density matrices, we can better understand the behavior of quantum systems and use them to perform powerful computations. We can decompose the density matrix and observe that it is equivalent to a combination of the identity matrix and Pauli matrices. We can represent the Pauli matrices using a three-dimensional vector sigma, while V represents a unit vector on the block sphere. If we use I, X, Y, Z as the basis, then ρ is isomorphic to quaternions. A unitary transformation is a type of matrix that acts on a quantum state to produce a new quantum state. We use the symbol U to represent the unitary matrix, while U dagger represents the conjugate transpose of the matrix, and both satisfy the mathematical relations that the transpose conjugate of the unitary matrix multiplied by the unitary matrix equals the unitary matrix multiplied by its transpose conjugate, which equals the identity matrix. If a unitary transformation is applied to a quantum state ket psi 0, the transformation of the state can be represented by the matrix U. We can further extend this concept to describe the evolution of the density matrix using unitary transformations.